Welcome to Brain Vision.
Hi everyone, we're going to be looking at a problem dealing with mass flow and conservation of energy. So what we have is an air conditioning system where the initial mass of R134A in the container is 5 kilograms, which is at 24 degrees C. There's a valve that's opened, and it is left open until the mass is equal to 0.25 kilograms in that container. What we're asked to find is the quality of R134A and the total heat transfer, assuming that the entire process is isothermal. So what we're going to do is define our system, so we can actually define the tank as our system. And the energy balance is going to be defined as the following, where the energy in minus the energy out is equal to the change in energy of the system. And we can actually go ahead and plug some of these quantities and plug in for some of these quantities and say that the heat transfer minus the mass that's leaving and the enthalpy that's leaving is equal to the change in energy, which is going to be M2U2 minus M1U1, and M2 is the mass that's in the tank at the end, and M1 is the mass that we're starting with. So we can also do a mass balance and say that the mass coming in minus the mass coming out is the change in mass of the system, and we know that the mass exiting, which we're just going to call ME, same as here, is going to be equal to M1 minus M2, which is following the same designations we described before. So from the refrigerant table, A-11, so at the temperature T1 is equal to 24 degrees C, U1, which is equal to the internal energy, is going to be equal to UF, which is equal to 84.44 kilojoules per kilogram. And then we have our specific volume, V1, which is again equal to VF, which is equal to 0.000826 meters cubed per kilogram. And then we have our enthalpy, HE, which is equal to HF, which is equal to 84.98 kilojoules per kilogram. Now we can use everything at the same temperature because our assumption is that this entire process is isothermal. Next, what we're going to do is actually just solve for the volume of the tank. We know that the volume is equal to the mass times the specific volume, and we know these quantities at time 1 at the initial. So we can just go ahead and plug in our mass at the initial at 5 kilograms and our specific volume we looked up in the table. And we'll see that the total volume of the tank is 0.00413 cubic meters. And we can actually use this to find the specific volume of the tank at the end when the valve is closed by saying the specific volume at 2 is equal to the total volume over the mass at 2. And this is just a definition of specific volume. And we know we just solved for the total volume, and we know the mass at the end because that's given to us. And we'll see that the specific volume is equal to 0.01652 cubic meter per kilogram. Now, the final quality of the refrigerant of R134A can be defined as the following, and this is just from the definition. Where the X2 is going to be equal to specific volume at 2 minus the specific volume F over specific volume G minus specific volume F. Now recall that these quantities are just taken from the table itself. What we're going to do is from the table at T2 is equal to 24 degrees C, so remember isothermal, we'll see that Vg is equal to 0.031869 meters cubed per kilogram. We'll see that UFG is equal to 158.68 kilojoules per kilogram. And what we can do now is actually just use these quantities and solve for X2. Now, X2, as I said before, was V2 minus VF all over Vg minus VF. And we know these quantities from the table. And we know what specific volume at 2 is, and we can see that the actual quality at the end is going to be 0.5056. Now, to solve for the total heat transfer, we need to understand what the specific energy is, internal energy is at time 2. And that's where that UFG that we solve for and the quality can be used. Right? So we can define specific energy at 2 as equal to UF plus X2 UFG. Remember, these are all in the saturation state. So we know these quantities. We know UF, we know X2, we know UFG, and we can find that U2 is equal to 164.67 kilojoules per kilogram. And now we can solve for the total heat transfer by isolating Qin in that energy balance we did before, and say that Qin is equal to M2U2 minus M1U1 plus M1 minus M2HI. Now, we know all these quantities. We know M2, M1, because those are given to us. U2 we just solved for. U1 we looked up in the table. M1, M2 are the same thing. And HI we also looked up in the table. So knowing all these quantities, we see that Qin is equal to 22.62 kilojoules. And that's our final answer. And the quality that we solved for before is 0.5056. And that is also our answer.